Good morning, everyone. My name is Natalia Korcz-Konkol, and I am pleased to present the article titled Stabilizing Forces in Trapezoidal Sheeting Used as a Part of the Bracing System. In the analysis of bracing systems, global geometrical imperfections of the restraint elements should be taken into account. A possible routine to complete this aim is direct implementation of the initial imperfection in numerical analysis. This method has significant drawbacks. Building an imperfect geometry is not as simple as building an ideal one. What's more, the geometrically nonlinear analysis means higher software and hardware requirements and longer computations. Especially the first aspect is the reason why this approach is not popular in engineering practice. Fortunately, another well-known approach, which is a great simplification of the design procedure, can be found in Eurocode 3. According to this method, the initial bow imperfection of the braced element is replaced by the equivalent stabilizing force. Currently, also alternative suggestions of stabilizing force calculations can be found in the literature. It should be noticed that all these procedures concentrate on bar bracing and neglect roof cladding. In the presented paper, part of the steel single-story building with truss girders, purlins, and trapezoidal sheeting was analyzed numerically in two variants. In case 1, bar bracing was considered and the corrugated cladding was neglected. In case 2, it was assumed that the trapezoidal cladding is a structural member and a part of the bracing system. The main objective of the research was to compare the forces stabilizing the upper truss cord in case of diaphragm bracing with the case of bar bracing, using direct numerical way of considering initial imperfections of the truss girder. Additionally to numerical analysis, the outcomes of the three selected analytical procedures were used for comparison. The study subject was a pitched roof structure. Part of the roof, consisting of 3 trusses, were extracted for the analysis. The trusses were 24 meters long, with non-uniform depth and 6 meters spacing. Z-purlins were located every second truss join in 2.4 meters spacing. Trusses were supported according to the scheme presented in Figure 6. Numerical analysis was conducted in Abacus software. Shell elements were used in order to address structural aspects neglected in the literature-based analytical and numerical calculations. Two variants of bracing were taken into consideration. In case 1, the bar bracing was built from flat bar tension members. In case 2, the roof decking resting on purlins and made of trapezoidal sheeting was considered as bracing. The load, corresponding to self-weight of the trusses, was applied to all truss members. The snow load was taken into account as the reaction forces from the purlins to the trusses. The purlin cord connection was realized using L-shaped connector, which was welded to the cords and connected to the purlin using the group of bolts. In numerical models, tie connections were used. Reactions from the purlins were applied to the vertical parts of the purlin cord connectors as attraction. The purlin sheeting connection in case 2 was mapped by means of tie connections, so the flexibility and the scheme of the fasteners were neglected. In order to create structural geometry with an initial imperfection, the linear buckling analysis was performed. The buckling mode was exported from the results. Next, the mesh with the imperfection was imported to the target model in order to perform static analysis including geometrical nonlinearity. The magnitude of the imperfection was assumed equal to the value from Eurocode procedure. Eurocode-free procedure to assess the equivalent stabilizing force, two main assumptions hold. The initial geometrical imperfection of the restraint member is the parabolic bow imperfection, and the value of the compression force in the braced element is assumed constant. Regarding these assumptions, the equivalent stabilizing force and the stabilizing force in purlins can be calculated. In the alternative procedure number 1, the same shape of the geometrical imperfection is considered. However, it's noticed that the value of the compression force in the braced element is not constant but varies within truss span according to quasi-parabolic formula. Finally, the equivalent force can be calculated. Here, we can see the differences between the value of equivalent stabilizing force according to Eurocode procedure and according to alternative procedure number 1. In the alternative procedure, it's also noticed that the Eurocode isolation of the upper chord from the truss is not correct. That is why additional component of the stabilizing force due to the distortion of the truss girder is considered. The force is the result of the initial bow imperfection of the upper truss chord. In the alternative procedure number 2, two components of stability forces are taken into account. Step-changing compression force in the imperfect upper chord of the truss and the distortion of the truss girder. The difference between this method and the alternative method number 1 is in the way of calculating the stabilizing forces. This method is based on the analysis of the force equilibrium in nodes. Values of the axial forces in purlins obtained in analytical and numerical analysis are presented in Figure 9. The results confirmed the literature-based outcomes achieved for bar bracing, that the values and the distribution of the stabilizing forces in the roof differ significantly from the values obtained according to Eurocode procedure. The maximum axial force in the purlin in case 1 of the numerical analysis was circa 2.5 times larger than the value obtained according to Eurocode procedure. According to the alternative methods, it was about 2 times larger. Numerical analysis confirmed the shape of the graph of the axial forces in purlins obtained for alternative procedures. However, the values of the forces differ. Discrepancies possibly result from at least a few aspects included numerically, thanks to using shell, not bar elements, but omitted in the analytical procedures, such as the flexibility of purlin truss connections, the eccentricity between structural elements, building numerically an entire truss with a bottom chord and diagonals, or the fact that purlins and bracing were not infinitely rigid in numerical model. Other factor which may produce discrepancies was that numerical results were achieved for the case of pitched roof, and that is why the axial force in ridge purlins is lower than in the neighboring ones, and it may even change the sign. Different responses of two bracing systems were observed. In general, the axial forces in purlins in case of diaphragm bracing are lower than the forces in case of bar bracing. This tendency was observed although the purlins were braced by sheeting, so they provided a more rigid support for the trusses. It means that trapezoidal sheeting bears a significant part of the stabilizing forces. Summing up, numerical analysis was conducted in order to observe the forces stabilizing the upper truss chord in two variants of bracing system, bar bracing, frequently considered in the literature, and diaphragm bracing, in roof purlins. We are not aware about any published studies of the second variant in the view of stabilizing forces. What's more, results of three analytical methods to compute the stabilizing forces were used to the comparison. Complex numerical models allow to provide the computations with the factors neglected in the analytical procedures and in numerical models adjusted to beam elements. A few aspects were pointed which should be considered in further scientific works in order to find new simplified procedures practical in engineering approach and including all important factors. Thank you very much for your attention.